1111.
I must start by thanking the translators because this has been an excellent meeting to be able to listen to the talks, especially the previous talk. So I come from Cloudflare. We announced on April 1st, which is usually April Fool's Day, a new resolver. There's various things that I would like to talk about today. I have a lot of slides, but I'm going to jump through some of them. I'm going to talk a bit about the technology, and I'm going to talk a bit about the cleanliness of this IP address. In fact, two IP addresses that I'll talk about. We focus on privacy, so I have a few slides on that. But indulge me if I just show you a quick picture of our network, the number of locations. In fact, we're here in Moscow as well. This is a very large Anycast network. Everything that we do is one set of addresses that are announced everywhere. So for the resolver, it's the identical thing. We brought up a public resolver on 1.1.1.1, and we announced it at every dot that you see on this map. We had particular ideas in mind as to what we wanted to build, why we wanted to add yet one more resolver to the world. And really, ultimately, this focus on privacy and some of the new RFCs was very high on our list. DNS, as I'll talk about, is a very leaky protocol. In fact, we had a talk earlier today specifically that used this, and somebody asked a question from the audience that said, won't DNS over TLS or HTTP cause that type of study to be ineffective? And I'm quite happy to say yes. So let's talk about two of the features that are there before we talk about that. Query minimization. So DNS is a wonderfully old protocol. We have all used DNS. In fact, more importantly, everybody in the internet uses DNS. And luckily for the general public, they don't notice that's important. They either open an app or a website and they put a name in and it replaces it with the appropriate binary addresses that we then in the underlying software use. But DNS, as I said, it's a very messy old protocol. It's chatty, which means that if I want to take a particular address and I want to translate it, I actually send the whole URL in its whole length to everybody that's involved in answering that question. DNS is hierarchical, so we know that we start with dot, and in this case we have a .com and then a particular secondary zone, but each one of them gets that. In QNAME minimization, the root just gets asked, hey, where's com? Because that's all you need to know. In the secondary zone, when you find that, you just ask for dub, and that's the end of it. So this is a very long overdue change. It has bugs. It has absolutely found DNS servers that didn't expect this. The RFC was on, these slides are uploadable. The RFC is there, and there is in fact some very good papers written on some of the problems with this. But it is the most logical way to go to reduce the sort of the leaking data that exists in DNS. The other one that's really interesting is in a world of DNSSEC, when you sign information and you have inside the DNSSEC world this ability to say that something doesn't exist, part of the proof that something does exist. You can in fact use that cache, you can use that information to even more aggressively stop querying and reduce the leaking of questions. DNSSEC is an authentication protocol. It's not an encryption protocol. It doesn't encrypt the data, it just simply authenticates the data. And so with query negative caching, we actually have this ability to reduce a query. If we know something doesn't exist, then we actually know that many other things don't exist at the same time. This one's a really complicated RFC to read, by the way. The DNS has got quite complicated in that sense. But let's go hit the fun parts here. So DNS over TLS is exactly what you're doing with websites that are encrypted with an HTTPS environment. You're wrapping a standard communication into a TLS environment where the whole public key PKI is used for providing secure communication. It just hadn't been done for DNS. And this is different than DNSSEC, as I said earlier. It is simply the ability to have a secure path from an end user, a stub resolver, to a resolver and onwards. So it really does stop the ability to see what the DNS query is. Interestingly, DNS over HTTPS just seems wrong, doesn't it? Think about what we're doing in the internet. We implemented UDP for those quick, fast queries, and then we implemented TCP for those long-standing transfers. That's a very simple simplification. We've moved the web access now with quick to sort of saying, oh, UDP is the way to go to move web pages. And now in the DNS world, we've said, hey, HTTPS is the way to move DNS queries. There's something wrong with this, except for stay tuned, because with HTTP 2 and channeling and the like, this is going to start really be useful in the future. The last thing, not the last thing, but to talk about security, you have to ask, who am I asking a question of? So we deal with privacy in a data policy inside our company. And we simply say that we throw away all the data after 24 hours. We actually don't even store things like the IP address of where you're querying, because that can already be obfuscated inside the server before it ever hits a log or a database or anything. And so the IP address that you're querying from already gets, let's say in the v6 world, gets shortened to a 48. In the v4 world, gets shortened to a /24. The 1111 address has some interesting history. I'll talk about that in a second. But to explain part of this, we also have a deal with APNIC. That's where these addresses got assigned from. And so we share data with them, but we only share it after obfuscation. And in fact, that's actually a whole other environment. It's so much data that we don't actually forcefully share it. The deal is very simple. The data is there for 24 hours. It's already obfuscated. If APNIC grabs it for their research, because this is a research address, they do. If they don't get it, it disappears. There's so much DNS data in the world that if you want to do something, you don't really need every single solitary bit. So that's actually a rather nice feature. Once it's gone, it really is gone. And we've got some audits in place for this, but that's all the fine print. So let's talk about those IP addresses. The v4 ones are the interesting ones. These are two addresses that quite a while ago somebody said, these are not usable addresses. There's noise. People have built them into their networks as a test environment. You'll see why. And I will tell you right now, if you're staying at this hotel and you're using the Wi-Fi on this hotel, you can't get to 1111. This is a hotel that has a piece of equipment somewhere configured with 1111. Now, I happen to know what that equipment is, but that's not the point of the conversation. It's actually much harder, by the way, to do v6 addresses that are cute and easy to remember. C'est la vie. But this is why this address is so much of a problem. A major hardware vendor specifically teaches you to use addresses like 1111. It's there in the book on many, many pages. The other example the other example IP address there is 2.2.2.2. That address is assigned to Orange, France Telecom, by RIPE. They've got exactly the same problem. This 1.1.1 address is just simply polluted space. But how polluted? By the way, I didn't mean to say who the major hardware vendor was on the previous slide. But I had no option. But it gets worse. This is a user on a random Linux bulletin board who simply says, it's too much effort to type 192.168. I'm just going to use 1.1.1. And what's wrong with that? The beration, this thread continues for quite some time. He is clearly wrong, by the way. Independent of what we're doing, he is clearly wrong. But IP addresses are assigned. There are addresses for documentation. There are addresses for private use. This type of usage is quite excessive. But he's not alone. Here's a partial list of hardware vendors that do home gateways that have 1.1.1.1 built into their software. The list probably is much larger. It isn't just one box or two boxes or 10 boxes. These boxes are there in the millions, and they're all over the place. So when we went through this project and we said, quite frankly, we want a really easy address for everybody to remember, we looked at this and went, ooh, this is a problem. But it's even more of a problem because if you look at the partial list of telcos, think of the people you now have to talk to. But a lot of telcos actually have fixed it. This is 1.1.1.1 used inside a backbone. The nice guys at Kazakh Telecom, complete country black-holed from this address because they used it. We sent them an email. They fixed it. They didn't actually put it in permanently, so it unfixed itself. They sent them a new email. Done. Finished. ITC in Iran, exactly the same issue. I've got a couple of other examples in here. But these, yes, there are a few names that you recognize, but don't snicker, because you all know you've done it yourself. You've been in the test lab and you've typed in an address like this just because it's quick and easy. Well, keep in mind, when your network is BGP enabled, there's a possibility it'll leak. We'll talk about that in a moment. Here's an example from, I was in Senegal for the AFRINIC meeting about a month ago. And 1.1.1 was in use internally inside the network. I so happened to be sitting next to the engineer from that AS number. And I said, hey, you need to fix this. A couple of minutes later, fixed. That isn't really repeatable, but it's a good example. This graph, by the way, is the graph of our, I wish I had it before that, but as I told you, we only keep 24 hours of data, and I forgot to collect it. But the bottom line is that as soon as he fixed it, we realized that there was queries coming in. This is actually legitimate DNS queries. I'll talk about random traffic in a moment. Look, RIPE Atlas. How many times have you heard at this conference and previous conferences here, this is the greatest thing since sliced bread. It is superb. We used it to find all manner of problems. Most of those telcos were found via RIPE Atlas testing. What's interesting is that you can use RIPE Atlas to see some interesting data. I got a Yeah, so this guy here, whichever probe that is, was in fact responding very, very quickly. That's a great example of a CPE device that just responds directly as opposed to letting the bits flow. So we did quite a bit of testing on this, and we've written a blog post about this. The URL is at the bottom. But why was this IP address even available to us? And the answer is that it was 2 addresses that had been deemed impossible to use back in 2010. So this is a set of data, a set of testing that was done way back when. Both RIPE and Merit did the announcement of this IP address to measure what was there. There's some very good presentations on this. Google then followed up with another study for APNIC, and then finally we announced it about a week and a half before April 1st. This is what we saw. The previous studies were in the hundreds of megs. Oh, and then in 2014, a gigabit of data. We turned it on in 2018 and saw somewhere between 8 and 13 gigs of unrequested traffic. Just traffic that has just sitting there with one-way requests. No one was ever responding. They were probably following a default route to somewhere. But this is the noise. This is the traffic without us ever enabling a service on that IP address. You can see the time and date that we turned it on, about the 20th of March. We didn't expect this. The good news is that 10 gigs of traffic doesn't actually, that's tiny for us on our backbone or on our network, but it's still 10 gigs of traffic. So we actually spent some very early time tracking this down. So let's look at a couple of the stats. First of all, what ports? Predominantly, we're seeing web traffic to port 80 and 443. It's interesting because those SYN packets were never being responded to, and yet there was this much. The 8080, we're familiar with that from alternate websites. And then there's UDP traffic. Port 53, we're seeing DNS requests for this already, and these are the big numbers. And then we're seeing syslog. And this caused us an interesting problem. Somebody somewhere, and I don't mean single person, many people, have put 1.1.1 in their syslogs. Therefore, ASCII text of something important to their system is being sent randomly into the internet, unencrypted, and now that we've announced this address, we are receiving those packets. And we made a conscious decision. No one is going to look at them. Full stop. Because the last thing you want to do is phone somebody up and say, hey, you know, your Linux box is telling us that you've just changed your password. You don't want to do that. So other stuff, 1.0.0.19. There are millions of TP-Link routers out there using that as their DNS address. And all over the world. Why? Why? Let me ask again, why? Because we have not found out. To fast forward a little bit, about 2 weeks into running this on 1.1.1.1, we decided to actually roll up a DNS resolver on the .19 address because we knew we were going to actually help a large number of people out there. And that was within the bounds of what we decided to do, what we were trying to do. So we still don't know why. Okay, where's it coming from? Congratulations, China, you win. Here, nothing. Not really. You're off the radar on this one. And to be honest, China. There's no value in this graph, this pie chart, other than saying that. But this is the fun part. Why was that traffic pattern doing what it was doing? So at very specific times of day, now just a second here. we're still not responding to any packets on this IP address. This is one-way inbound traffic at this point in time. There is really no outbound. So here we are with these graphs that are changing with multiple gigabits inbound to us around the world in these different IP addresses in different ways. And some of them, by the way, a whole set of IP addresses. It just keeps going. The short burst stuff would be interesting if it wasn't for the fact that it repeats every single day. Memcache, we see a lot of attack traffic as well, but you know, at this point in the conversation, you realize that that's actually quite boring. It's the other stuff that you wonder what's going on. Okay, so we started to look down DHCP requests from Macau. You know. And then the bottom one here, which is actually the good part. The UDP requests, the DNS requests were very, very low. So one of the beauties of that was that we sort of knew, although the .19 address was much higher, the 1.1.1 was very low in this. So we knew we weren't going to get too much random stuff. So there are another couple of talks. Again, the slides are online, so grab the differences. We still see the iPerf traffic from 10 years ago on these particular IP addresses. And it makes you wonder, if this is just a study on a pair of /24s that are very easy to remember and easy to type in, I wonder what it's like on some of the other IP addresses out there that are either unused or just you haven't looked at. Okay, let's look at, I've got a couple of slides on what we've done. This is the up and to the right graph. We went from very little to a lot. We have a wonderful sort of user day in, day out type graph. This graph is probably about a month old, but it just keeps continuing. We keep aggregate stats on the service. In other words, we keep the counters of how many queries and the like. We don't keep any of the actual query names. That would be insane, actually, to do. We do keep the TLDs because it's sort of nice to know that. The source data is long gone, et cetera, et cetera. So this is how we get this graph. So let's talk about route leaks, because yesterday I was on a panel talking about routing and the like. We've talked about route leaks in other ways. It's a nice topic for everybody. So about a week ago, a network decided to announce 1.1.1.0/24. This is not the first time. This happens quite often. But this was the first time it happened inside our announcement of this address. It happened for about 30 to 60 seconds. That was the total length of the hit. It lasted longer on Twitter. It was discussed for days on Twitter. What's interesting, this is an RPKI signed route that was leaked via a route server at an internet exchange. And to go back and talk about something from yesterday, internet exchanges, let's talk about improving the filtering. That's not the only place, but it is interesting that we have a signed RPKI route, but we still dealt with a leak. And that's because signing is different than filtering. We have a long way to go in that area. Okay, a couple of slides on speed, then I'm done. We do a couple of tricks to make our DNS servers faster. So we do various things. We take lists like the Alexa Million, and we preload the cache. We take care of time to live. We also take care of geography, et cetera, et cetera. There are various other lists like the Alexa list that we use. We actually do a few other things. We actually look at a very rough log of what people are querying, and we make sure that that, on a geographic basis, is kept in the caches. So we want to keep the caches warm. We also run, this is all based on NOT from the guys in the Czech Republic. And we also have the ability for the resolvers to be restarted with a hot cache, which makes a massive difference at this scale. That's prefill. The other one is backend multicast. One of our data centers will contain racks and racks of servers. This DNS resolver runs on a ridiculously large number of servers. If you query something, example.com, onto one server, and then somebody else queries example.com onto another server, it's a different cache, it's a different box. So we use a back-end multicast mechanism so that when we get a resolver result, we use multicast on the back-end network to basically tell all the other resolvers what that information is. There's a whole bunch of stuff to stop this overflowing. There's some hysteresis in it to make it sort of not bounce around too much. But it means that resolvers, when you have a rack or racks and racks of 20, 30, 40, 50 servers in one location, they all get the answer very quickly. And it seems to work. It also means that we get, very good results to all of these. That one. So what's the results? The results are that we ended up, at least with DNS perf, at the #1 spot. We ended up very quickly, so we can do privacy and we can do speed. Yay us. But DNS actually makes a difference. That DNS query is everything that you need to work fast in order for that page to come up quickly, that first page when you generate a new site. Okay, right. About finished. I talked about easy-to-use addresses with the pluses and minuses, DOH and TLS for privacy. I think that our cleaning up of routing is something that's good for the internet. It's sad that we have to do it, but let's admit it. Every time you clean up something somewhere, something else must get better. That's all I have to say, except I have stickers if anybody needs them. Thank you very much.
Коллеги, вопросы к Мартину?
So, questions to Martin.
So the question is, can we get cool v6 addresses? Yes, but I don't think any of the RIRs would. We can request cool v6 addresses. No RIR will ever say yes.
I mean, within the ranges, right? I'm not saying 1 colon, 1 colon.
No, yes, it has to be within, yes. No one thought this one through for v6. There aren't that many cool addresses.
Quick, oops, it's on. Well, just a quick question. For logging, I'm Jaap Akkerhuis en dan het labs. For logging, you throw away the log files after 24 hours. But are you aware of the work Christian Huytema is doing? He actually has this probe, especially for these situations, where he actually uses the logging, does an aggregate of all the traffic, and so you never see the actual logs, but only the aggregate of all the traffic. So that makes life much easier to get some idea how things are going.
Yeah, our logging environment is probably worthy of a massive talk because there is large amounts of aggregation done right in the resolver before anything is sent into the logs. Actually, I should make a comment here. We are a big user of ClickHouse from Yandex, and so I don't know if there's anybody here, but thank you. It's superb code. And that's pretty much the only way that we can do even some of the queries into this. It's a massive amount of data, even if we have dealt with the aggregation and the privacy stuff right at the beginning. So I think there's a whole separate talk on the complexity of keeping private logs that should be given at some point in time.
Any other questions? No. Thank you. Thank you, Martin.